So students, can you hear me?
Yes, sir.
And you can see the sheet now. You can see the
Yes,
sheet.
sir.
Okay.
Yes, sir.
In the last class, I have defined the discrete and continuous random variables, how to describe the probability distribution of discrete and continuous random variables. So when you have a discrete random variable, you have a probability mass function. If you have a continuous random variable, the probability distribution is described by a probability density function. Also, you have a more general function called a cumulative distribution function, or the CDF of a random variable. We have shown the relationship between the probability mass function and the CDF. We have also shown the relationship between the PDF and the CDF. Then we also came across a case where we may have a mixed random variable. That means a random variable which partly is discrete and partly it is continuous. So let me just give one example here. So let me give one example here. Is it visible now?
Yes, sir.
Okay. So suppose I consider, say, x as the waiting time at a traffic signal. So of course, when you are driving on the road or you are traveling by a vehicle on the road, you find that sometimes there is a red light and then you have to wait for some time, and that waiting time can vary over a certain interval. For example, it may vary over 0 to say 1 minute or 0 to 2 minutes, depending upon the city and the local conditions that they are having. And sometimes when you are coming to the traffic signal, you find that there is a green light and you cross it. So it happens a number of times that you may have to wait, and it also happens a number of times that you don't wait. Now this is a classical example of a mixed random variable. For example, say 25% of the time you don't have to wait. So you may have, say, a probability that x is equal to 0 is, say, 1 by 4. And when you have to wait, then it is a continuous distribution, and you may have a density, say something like, let me put over an interval 0 to 0 to 1, and we may put the density again as say 1, and then you have to allocate the remaining probability, so 3 by 4, because 1 by 4 we have already put here. Okay. So if I write down the CDF for this, how it will be? CDF will become 0 for x less than 0. It is 1 by 4 for x is equal to 0. And after this, you have 0 to x dt. And of course, you have 3 by 4 for 0 less than x less than 1. And it will, of course, become 1 for x greater than or equal to 1. So I can combine this. I can write like this. It can be written as 0 for x less than 0. It is 1 by 4 plus 3x by 4 for 0 less than or equal to x less than 1. The case in second part and third part I am combining, and it is 1 for x greater than or equal to 1. So I hope this example is clear. Is this example clear?
Yes, sir. Yes, sir.
Now I just want to add here. See, yesterday towards the end I have introduced a concept of expectation. Now if I have a discrete random variable, expectation is defined as the value of the random variable multiplied by the probability, and then you sum over all the possible values, and provided the series is convergent, it is defined as the expectation. In the case of continuous random variable, you are multiplying the value by the density and then you are integrating over the region. Now if you have a mixed random variable, then here you have a PMF portion, this is PMF part, okay, and then you have a PDF part. So if I want to calculate the expectation of this random variable, then I will apply separately the definitions in both the parts and add the two. So here expectation will become 0 into 1 by 4 plus integral 3 by 4 into x dx 0 to 1. So of course this can be evaluated. So because this part is 0 anyway, and you get 3 by 8. So this is the mean of this distribution.
Sir, you are muted.
I think some students are interfering here. I mean, that should not be done actually. And another thing is that I have seen that whatever files I am uploading in the MS Team area, some students are modifying that. That should not be done because it will be a loss to the students only actually, if you change the files. So now if you see, I have uploaded assignment number 1 and its solutions. Today I have also uploaded assignment number 2 and its solutions. I have also uploaded a class test schedule. Okay. If you see carefully, their class test schedule is also uploaded there. So we will have first class test on 2nd, then we have on 16th February, then we have on some date in I think 16th March, I think 2nd February, then 23rd February, then 16th March, and I think then 5th or 6th of April. I have uploaded it there, you can see. And this is to be taken in the regular class hour only, because all of these are Tuesdays. So we are Tuesday class is 12 to 1. So we will conduct the Can you hear me now?
Yes, sir.
Yes, sir.
Yeah, I was just mentioning that actually some students are trying to interfere in the MS Teams actually, so that creates some problem because it's a very large class and everything is online. So if some student is doing that, then it will be harmful to all the students actually. So they should not do like that. I mean, I don't know why some students have changed the file which I have uploaded. What is the reason for that? So is there some student Shraman Pal?
Yes, sir. I mistakenly, instead of copying the files, I mistakenly moved them. That's why. The files themselves haven't changed anything. Sorry for that.
So you are muted again.
Can you hear me?
Yes, sir.
Yes, sir.
So I don't know, somebody is interfering. I mean, who is that actually?
So you can make all of us attendees the next time.
Okay. All right. So I was giving example of a symmetric distribution. So if you can see that the things are similar on both the sides, then it looks like a symmetric distribution. So you can have things like this. Okay. So I give a formal definition. A random variable x is symmetric about a point C if probability of x greater than or equal to x plus C is equal to probability x less than or equal to C minus x. So here let me put C plus x is equal to probability of x less than or equal to C minus x for all x. So if that is so, the distribution is said to be symmetric about a given point. In particular, if I want to say it is symmetric about 0, and of course in terms of density, you can see that the density at C minus x will be same as the density at C plus x. Or if it is a discrete distribution, then the probability mass function at C minus x is equal to the probability mass function at C plus x. So we will see later on if the distribution is not symmetric, then how it looks like and so on. Another thing is that expectation is a linear function. That is, expectation of ax plus b is equal to a times expectation of x plus b. We can also define expectation of any function of random variable also. Suppose x is a random variable and g is a function, then we can define expectation of gx as if x is discrete and it is equal to integral of gx fx dx if x is continuous. Of course, when we write this series and the integral, it is assumed that they are absolutely convergent. Yesterday, I have already explained to you the concept of expectation. So expectation, I explained to you, it looks like if I give an example from physics, then it is something like a point of equilibrium. That means if there is a say metal rod with certain density and it is hanged uh, with some weightless strings on both the sides, then what is the point of balance or the point of equilibrium? Or you can also call it center of gravity. And if it is a weightless string and the masses are attached at certain points, then what is the balance point or the point of equilibrium? Okay. So now this concept can be further extended. So in place of expectation of the random variable itself, I can talk about expectation of log x, expectation of sin x, or anything, because in general I can talk about expectation of gx. So of particular interest is the following. That means I can consider let us take say gx is equal to x to the power k. So mu k prime, that is expectation of x to the power k, this is called kth moment about origin. Okay, or it is also called kth non-central moment. See, suppose I have points like this x1, x2, and so on, xn, and on this the weights px1, px2, pxn are attached here, then sigma xi pxi is some such point here, which is the balance point. And in the case of continuous, so suppose this is your x, okay, at the point x you have the density fx, then x fx dx is this point. So I hope this idea is clear to you now. We usually denote mu1 prime, that is expectation of x is equal to mu, okay, called mean of random variable, okay. So in general I am defining expectation of x square, expectation of x cube, and so on. Of course, k can be taking negative values also. I can put k equal to -1, I can take k equal to -2, or even I can take k is equal to 3.2, or I can take k is equal to square root 2. K can be anything, but of particular interest will be integral moments. That means the moments with integer powers. Okay. Now if I use this one, then I can consider mu k, that is expectation of x minus mu to the power k. So mu is the first one, first non-central moment. Then this is called kth moment about mean or kth central moment. Now we have certain useful interpretations from here. So for example, what is the first central moment? It is expectation of x minus mu. Because of the linearity, we can put it as this, which is nothing but 0. So the first central moment is always 0. What is the physical meaning of this? See, when we are considering the values x minus mu, so in case of discrete, it will look like xi minus mu for I is equal to 1, 2 and so on. So what we are saying is that you will have negative values and you will have positive values. And when we take the weighted average, it will become 0. So that means what I am saying, sigma of xi minus mu pxi, that is 0. Similarly, in the case of continuous, you will have x minus mu this is equal to 0. So basically what we are looking at, see, suppose this is mu and you have values distributed here, x1, x2 and so on, xn minus 1, xn and so on. So we are interested in the deviation from the mean. So what is the average deviation from the mean? It is always 0. So now we can look at some other values. If we still want to see, for example, I look at this one. Let me plot 2, 3 values only. Okay, suppose I just take, this is the mean and I plot this. Okay, let me take another one. Okay, this is mu. So let us look at this graph 1 and graph 2. And this is your x1, x2, x3, x4. And here you have x1, x2, x3, x4. So if you look at the figure 1, in the figure 1, the difference between x1 minus mu, x2 minus mu, x3 minus mu and x4 minus mu. And if you compare it with the difference between x1 minus mu, x2 minus mu, x3 minus mu and x4 minus mu in the second figure, then you find that the differences in the second figure are higher. In the differences in the first figure are less than the differences in the second figure. But if I take expectation of differences, it will be 0 in both the cases. But still, how to give an interpretation to this, that in the second one the values are dispersed far away from the mean compared to the first figure. So we can look at the absolute differences. So we can consider, for example, expectation of mod of xi minus mu. So mod I need not put here because it is expectation. Okay. So then this is called mean deviation. So it is absolute mean deviation. Okay. Absolute mean deviation from mean. Okay. So this will give you an idea. That means in the figure 2, expectation of mod x minus mu will be higher than this value in the first figure. However, this mod thing is not mathematically very convenient. So what we do, we consider another one. We consider mu2, that is expectation of x minus mu square. That means we consider squared deviations. So this is called variance of x. It is denoted by variance of x. It is also having a usual notation, okay? Sigma square. Then sigma, that is square root of the variance, okay? This is called standard deviation. So if you have sigma square higher or sigma is higher, then the deviation is more. If sigma is less, then the deviation is less. So for example, if I consider these two distributions, so here suppose I say sigma 1 square is the variance, and here sigma 2 square, then sigma 1 square is less than sigma 2 square, because this distribution is more concentrated in the center compared to this distribution. Is that clear? Could you
Yes, sir.
understand this concept?
Yes,
Now
yes,
let
sir.
me look at, so first of all, see, I am defining two things. One is central moments and non-central moments. So of course, then one should have the direct relationships also, because this is just expectation of x minus mu to the power k. So if k is a positive integer, you can expand it, and then you can write this. So let us write down the relations also. So let us look at, say, mu k, that is expectation of x minus mu to the power k. Let us consider k to be positive integer. So this is then expectation x to the power k minus kc1 x to the power k minus 1 mu plus kc2 x to the power k minus 2 mu square, and so on, plus minus 1 to the power k plus 1 mu to the power k. So since expectation is a linear operator, you apply it. So expectation of x to the power k, that is mu k prime, minus kc1 mu k minus 1 prime mu plus kc2 mu k minus 2 prime mu square, and so on, plus minus 1 to the power k plus 1 mu to the power k. So from the non-central moments, you can calculate the central moment. As an example, let us consider, say, mu2. Then mu2 is mu2 prime minus kc1, that is 2. So this will become 2. Mu1 prime and mu, they are same, so 2 mu square plus mu square. So that is becoming mu2 prime minus mu square. You can write it like this, that variance of x is equal to expectation of x square minus expectation of x whole square. Since mu2 is actually perfect square, this is greater than or equal to 0. This implies that expectation of x square is always greater than or equal to expectation of x whole square. You cannot have a negative variance because it is expectation of x minus mu square. So you are actually summing up or integrating a positive function. Therefore, it should always be non-negative. You can have a reverse relationship also. Mu k prime, if I consider it is expectation of x to the power k, that is expectation of x minus mu plus mu to the power k. So this I can write as expectation of x minus mu to the power k plus kc1, x minus mu to the power k minus 1 mu plus kc2, x minus mu to the power k minus 2 mu square, and so on up to mu to the power k. So if you apply expectation linearly, it is mu k plus kc1 mu k minus 1 mu plus kc2 mu k minus 2 mu square plus and so on mu to the power k. We can define the absolute moments also. So beta k prime, that is expectation of modulus x to the power k. So that is kth absolute moment about origin. And if I define beta k, that is expectation of mod x minus mu to the power k, that is kth absolute moment about mean. And I had already given to you beta 1, that is expectation of mod x minus mu, that is the mean deviation about mean. We also define factorial moments. That is alpha k, that is expectation of x into x minus 1 and so on up to x minus k plus 1. Is it okay? So we have defined several measures here, and let us look at, say, the distribution, say, tossing of two fair coins.
So,
Okay, and yes,
so what does alpha signify?
yes. No, alpha k is the factorial moment, kth factorial moment.
So, what's
So
the
alpha
significance
1 will
of it?
become, alpha 1 is expectation x, alpha 2 is expectation of x into x minus 1 and so on. Yeah, actually when we will do the calculation of the higher order moments for integer valued random variables, then you will see that many times it is useful to calculate factorial moments because it is easier. And then from here, because again there is a relationship. If I am having, for example, alpha 2 is expectation x square minus expectation x, that is mu 2 prime minus mu 1 prime. So there is a direct relationship here. So sometimes for evaluation of higher order moments, factorial moments are more helpful, as you will see when we will do specific distributions in the next class. Okay.
Okay, sir.
So as you can see, the mean is important, the variance is important, or the standard deviation is important because it gives certain information. So why do we study moments? Because it tells something about the central tendencies. Okay. So central tendency of the raw values, that is expectation. If I look at the central tendency of the deviations from the mean, then we look at the variance or the standard deviation, and then we will look at some other things also. As I just proceed, let me firstly just take some example just to work out one or two things. So suppose I look at the number of heads. So what is the probability that the number of heads is 0? That is 1 by 4. What is the probability that the number of heads is 1? That is half. And what is the probability that the number of heads is 2? That is again 1 by 4. So this is a perfectly symmetric distribution. Okay. You have 0, 1, 2. So this is your 1 by 4 and this is your half. Okay. So what is expectation of this? It will become the central value because 0 into 1 by 4 plus half. So you will get the mid value. 0 into 1 by 4 plus 1 into 1 by 2 plus 2 into 1 by 4. So that is equal to 1. So for example, what is the variance of this? So let us calculate it. So for calculation of the variance, I will require expectation of x square. So that is again 0 square into 1 by 4, then 1 square into 1 by 2 plus 2 square into 1 by 4. So that is 3 by 2. So what is variance of x? Variance is 3 by 2 minus 1 square, that is 1 by 2. So sigma is 1 by root 2. Okay. Sigma is 1 by root 2. That is the average deviation, you can say, from the mean. So if you want to look at the this one, it is approximately 0.71. Okay. Now let us look at another distribution. Let me just take another discrete case. Okay. Let me put suppose a store has 10 ACs and 3 are defective. A consumer buys 2. So he selects 2 at random. So let us say X is the number of defectives in his selection. Then what are the possible values of X? X can take values 0, 1 or 2. What is the probability of X is equal to 0? That will become 7C2 divided by 10C2. So you simplify, it is becoming 7 by 15. What is the probability of x equal to 1? It is 7C1 into 3C1 divided by 10C2. Well, again it is again it is 7 by 15. And let us take, say, what is the probability of x equal to 2? Then it is 3c2 divided by 10c2. So that is 3 by 55, so that is 1 by 15. So if I plot this distribution, how it is looking like? At 0 you have 7 by 15, at 1 you have 7 by 15, and then you have 1 by 15. Okay, 0, 1, 2. This is 7 by 15. Naturally, here you can see it is not symmetric distribution. If I look at what is expectation of x, so that is 0 into 7 by 15 plus 1 into 7 by 15 plus 2 into 1 by 15. So that is equal to 2 by 7 plus 2, 9 by 15. That is 3 by 5. That is 0.6. So the balance point here, it is coming somewhere here. Okay, this is expectation x, 0.6. Let us look at what is expectation of x square here. So that is 0 into 7 by 15 plus 1 into 7 by 15 plus 4 into 1 by 15. So it is 11 by 15. So what is variance then? That is mu2 prime minus mu square, that is 11 by 15 minus 9 by 25. So you can easily calculate it. It is approximately 0.37. Okay, I mean you can write it as 28 by 75 actually. I have just written in the numerical terms to give an idea. So you can see the values are 0, 1, 2. See, to a layman it will look like that the deviation should be 1 from the mean, because he will put 1 as the central, and or even if you put say 0.6, then minus 0.6 and then 0.4 and then 1.4. But the average deviation, so this is square deviation. If I take the square root of this, then it is becoming 0.6. Okay. Now another thing which you may like to explore now, see if you compare these two, these both are discrete here, but this is giving you a symmetric feeling that it is symmetric, isn't it? Around the midpoint here, but this one is not so. It is not symmetric, isn't it? So if it is not symmetric, then what is the measure for that? So we look at asymmetry or skewness. Are the calculations clear to you for the previous exercise? I have just done a very elementary type of calculations. Did you follow the calculations?
Yes, sir.
You are able to follow the calculations, no? So now let us
Yes, sir.
look at it. See, so I have made 3 curves here. Okay, so the middle one is a symmetric. However, the curve which is on the left, it is having a very thickness in the left side and a tail which is longer on the right side. Okay. This is known as, so if it is asymmetric, it is not symmetric, so it is asymmetric. It is also called skewed. Okay. If it is a skewed distribution and you have a tail on the right, long tail on the right, then it is known as positively skewed. Okay. Positively skewed. On the other hand, if there is a long tail on the left side and there is a thickness on the right side, then it is known as negatively skewed. So we can just look at the practical thing. That means where these kind of things are happening. So I have just made one curve like this. Okay. Suppose this is x, this is okay. So let me put here fx, and x is actually distribution of marks in a competitive exam. So in a competitive exam, you know, for example, this your JEE or GATE or any other kind of competitive exam, UPSC, the number of candidates is very large. Okay, say 10 lakh candidates appear or 15 lakh candidates appear. However, only 1 to 2% students qualify. So the qualification is somewhere here. Actually, what happens that you find very few people score high marks. So suppose you put certain cutoff, then very few people actually cross that thing. And most of the people, because you cannot select all of them, the number of seats are limited. Therefore, most of the students will be having marks below that cutoff. And a lot of students, they score actually very low marks. So at the bottom, there is a big chunk of things. So this is a perfect example of a positively skewed distribution. Most of the income distributions in developing world, they are actually like this. Hello. No, actually, I'm in a class. After the class. So if you consider, say, income distributions, okay, suppose Y is the income distribution. Then you will find that it will be something like this. Okay, because very few people have very high income and most of the people will be in the lower income group. 80 to 90% of the people are in the lower income group, and 1% people will be in a very high income group, or even 0.1% people, and then between say 80 to say 99% of the people, so that they will be in a middle income group kind of thing, and most of the people will be in the lower income group. On the other hand, we can consider so suppose I consider age or longevity. Okay, and suppose it is going up to say something like 100 years. So we put some scale here. Okay, starting from 0. So this is age distribution. So if you look at the age distribution, then any given country, you will find, I mean, for example, let us consider say a country like France or Germany, then you will find lot of people are in the middle to high age. Okay, that means that there will be a lot of people with 70 age, 80 age, 85, and so on, and there will be few people in the bottom. So this is a very good example of negatively skewed distribution. So now the question comes about the measurement of this one. So you look at again the differences. If you look at xi minus mu or x minus mu, we have seen for a symmetric distribution, expectation of x minus mu, I mean for any distribution, in fact, expectation of x minus mu is 0. So this does not give an idea. And if I take a square, then the positive and the negative part will not be known. So the next best thing is to use the third one. Okay. So for measuring the an empirical measure is using the third moment. So we give some notation here. It is mu3 divided by sigma cube. Okay. Sigma we have already defined. We can write like this, mu3 divided by mu2 to the power 3 by 2. Okay. So beta 1 is equal to 0 for symmetric distribution. It is greater than 0 for positively skewed distribution, and it will be less than 0 for negatively skewed distribution. So when we will do specific distributions, then we will work out these for that. So beta 1 is a measure of skewness. Let us also look at another type of differences that may look in a distribution. So I have just made some curves here. So if you look at this particular curve which I have made secondly, it is concentrated more towards the center. That means the tails are very heavy. Okay. On the other hand, I may have the tails are very thin. Okay. So this property, it is called kurtosis. So this is normal. Okay, this curve is normal. Now compared to the normal, if you look at the curve which has a higher peak, and so that means the tails are very heavy, this is called high peak, or it is called leptocurtic. And the one which is having very thin tails, it is called platycurtic. Peakedness. A measure for this is in the terms of the fourth central moment, mu4 by mu2 square minus 3. So it is equal to 0 for normal peak, greater than 0 leptocurtic, and less than 0 for platycurtic.
Sir, I have a doubt, sir.
Yes, yes.
Sir, how do you decide
Yeah,
upon
please
a
ask.
like what is the
Yeah,
criteria?
so the normal curve is actually the name of a distribution. So later on, I will be actually talking about the specific distribution. So the normal curve refers to the curve of the normal distribution. So we will come to that thing, and so the peaks are compared with respect to that. Okay. So normal does not mean a English language word normal. It means the peak of the normal distribution. So when I do specific distribution from the next class, I will talk about that. Okay.
Thank you, sir. Thank you, sir.
Okay, so I think I have to halt here. So there are few more characteristics of the distribution, that is the median and then the moment generating function, etc. But I think I will be covering it in the next class. Okay. But anyway, I have already uploaded the assignment, so you can start solving the problems from there. Okay. Actually, these assignments are given for you to practice about the problems, and I have already given you the schedule for the class tests. So we will have several class tests, and uh, in each class test there will be several problems, so you have to solve them. So unless you do practice, you will not be able to solve. So you please uh, solve these problems, as well as you can also solve some other problems also. Okay. Because solution of the problem is very much required for uh, understanding the concepts. Okay.
So
Sir?
will we have any doubt sessions?
Yeah, we can have doubt session. Yes, why not? So maybe in the next class, see, next class is, can you hear me?
Yes, sir.
Yeah. So in the next class, we can have doubt clearing also after I complete this median and other this characteristics. And then we can have some doubt session for some time. Okay. But you should solve the problems. If you don't solve the problem and only ask me to solve, then that is not much use. Okay. You should solve the problems. I already given, so you please solve those problems. Okay, then I think it is time to
So can
stop
you
the
tell
class.
what
Okay.
platform you are going to be using for conducting the exams?
I think it is Moodle, because I have already talked to this person in the CET. So they said Moodle they are able to conduct it smoothly. So
So, but can
we
you
will
please
use
look into
Moodle.
it, because previously when we used Moodle, we were facing very big issues like navigation was very slow and questions didn't load correctly. So
Yeah, anyway, all those things will happen. So if there is a problem, then you tell, because I mean, something we have to do, and if there is a problem, we will look into that. I mean, I cannot tell in general that what problem will occur or what will not occur, because this is an online thing. So there will be some problems. We cannot say, like, when I am speaking, somebody is muting me. So what can I say about that? Or somebody is changing my file. All those things will happen. So you please take the exams, because if you don't take the exam, then how will I grade? Okay. So you take the exam. Some people may have some problem, but we'll look into that. Okay. But I cannot assume that everybody will have a problem, because in the last semester I conducted everything and there was not a single problem actually. Everybody could submit everything and I could evaluate properly. So there was no problem. Only thing is that your class is much larger compared to the last semester. So because there are 939 students, so it's a much larger class. So fine.
so will everyone
So
give the
let
exam
me.
at the same time? Like all 939 students will log into Moodle at the same time.
Yeah, yeah. Yes.
So I think
Yes,
that
yes.
would be an
It will
issue,
be
because
at.
when we gave the exam for around 200 students in the previous exam in the previous semester for different courses, the Moodle used to lag at that time also, and now it's 939, and I think that will be a very big number.
Okay, so because this person told me that he has been able to conduct it smoothly, so that's what. Because I thought of conducting in different sets of students, but he said it is not a problem. He was able to conduct. So we'll see if there is a problem, then we will move to some other session. Because right now, if we conduct together, it is giving me flexibility of not using any extra slots. I am just doing it within my class itself. So because there is another type of complaint which is coming quite frequently, every day I receive emails that many students are telling that, sir, we have so many exams and even the weekends we are not free, and all those kind of complaints are there. Because if we want to do it in a staggered way, then we have to use some times on Sundays or Saturdays and all that time. So then again another set of complaints will come. So let me see if this is successful, fine. Okay.
Okay.
Sir, can you save
If
the
it is not
recording?
successful,
I
we'll
mean,
see some other. I don't know. I mean, here I am seeing some student is doing some recording. I can see some messages here, so I don't know. Is it